right, lovely to see you again. So we are doing lesson 11.2, 11.3. We are going to start out with a new proof for the Pythagorean theorem. And we will start with this right triangle. And we're going to say that we have, the given is right triangle ACB. And I want to prove that a squared plus b squared equals c squared. Here's my a, my b, and my c. So I'm going to use what we have with the corollary 1 to theorem 49 to prove this. Again, start with our given. Let's say that this is our altitude CD. And I'm going to label these two segments X and Y. And I'll start by using actually the legs and those segments. So I'll start with X over A is going to be equal to A over the hypotenuse. And Y over B is equal to B over the hypotenuse. Corollary 2, theorem 49. Next step, I'm going to cross multiply. And I will get CX equals A squared. And CY equals B squared, multiplication, and I hope you see Y. I think I heard groan, okay. Let's combine these two, and we'll get CX plus CY equals A squared plus B squared, addition. You'll notice on the left that I have C in both of those, so I can take out the C. Factoring. X plus Y is exactly equal to C by theorem 1. Add two segments to get the whole segment. Plug that back in. By substitution and simplify. So we know the Pythagorean theorem. There are also numbers, if you have three integers that fill into this, that's actually called a Pythagorean triple. A Pythagorean triple is three integers that form the sides of a right triangle. Remember, integers are positive whole numbers in this case, so something like 3, 4, 5, 6, 8, 10. Those would be Pythagorean triples. This takes us to just section 11.3, and we'll start with theorem 50. Theorem 50 is a shortcut for using right triangles, and it makes things a little bit simpler. And it's also called the isosceles right triangle theorem, or even sometimes 45-45-90 triangle theorem. And what it says is, in a right isosceles triangle, The hypotenuse is square root of 2 times a leg. And the proof is pretty simple, and you'll see it probably a couple of times. Here's our isosceles right triangle. We're going to say given is isosceles right triangle ABC. We want to prove that C is equal to A times the square root of 2. So we're going to start with isosceles right triangle. Use the Pythagorean theorem to say that a squared plus a squared equals c squared. We can combine the a squareds, so we have 2a squared equals c squared. I would just call that simplify, could be addition. Simplify is probably better. Early on, we had something called property of square roots. I'm going to do the same thing here, where I take the square root of both sides. And then when I finally simplify, I'm going to have c equals a square root of 2. Simplify. Fairly easy proof, and you will see it again. So how do we use Theorem 50? Well, like I said, it's kind of a shortcut for finding missing sides of right triangles. The easiest case is, let's say we have a right triangle that's isosceles, and this leg is 3. Well, if that leg's 3, we know this leg is also 3. If I want to find x here, I'm going to take 3 times the square root of 2. It really is as simple as that. If you got the leg, the hypotenuse is just whatever the leg is times the square root of 2. Do not make this difficult. Isosceles right triangle, 7. What is the hypotenuse? 7 times the square root of 2. There is nothing more to think about it when you've got the leg. Now, if you have the hypotenuse and not the leg, let's say for example I've got, this is 6. There's a little more work to it. What you want to do is set it up as an equation. So, I know 6 is equal to the leg times the square root of 2. That's the equation I have. So to solve this, I'll do y is equal to 6 divided by the square root of 2. Many of you right now, though, are saying, wait a minute, we can't have a radical in the denominator. And that's true. So what I'm going to do is I'm going to say y is equal to 6 over square root of 2, and I'm going to rationalize the denominator, which means I'm multiplying. This is just 1, but it'll make it look different. So I'll get 6 times the square root of 2. Square root of 2 times square root of 2 is square root of 4, which gives me 2. If I can further simplify it, then I do 3 square root 2. If I wanted to check that, I could multiply that by square root of 2 and I would get this. And again, since y is 3 square root of 2, so is x. That's the work you should be showing on the homework. So please don't just be giving me answers, because I want to see how you set it up and how you solved. Let's do one more. I want to find the leg. I know the hypotenuse equals the leg times the square root of 2. To solve, I divide by square root of 2. I don't want a square root of 2 on the bottom, so I'm going to multiply the bottom and top by square root of 2. This will give me 15 square root of 2 over 2. I can't do anything else with it. I'll just leave it like that. 45, 45, 90 triangle, or isosceles triangle. The corollary to this simply says the diagonal of a square is square root of 2 times a side. And the reason is, if we have this square, and we take the diagonal, which is this, all the sides are S, we split it into two 45, 45, 90 triangles, which means D equals S square root 2. Now we have one last theorem today, and I encourage you again, call me, you can call me even after the office hours. I will always be there during the office hours, but even later in the evening if you need to, you can call me. Theorem 51 is another special right triangle. We call it a 30, 60, 90 triangle theorem. And again, it's a kind of a shortcut. What it says is this. In a 30, 60, 90 triangle, the hypotenuse is 2 times the short leg. This is opposite 30, so it's the short leg. And the hypotenuse is always 2 times that. And the long leg is the short leg times the square root of 3. Which means this leg is x times the square root of 3. Let's do some examples. Short leg is 3. Hypotenuse is twice that. Long leg is short leg times the square root of 3. That's it. It gets a little trickier though if you do have the long leg. Let me show you. Let's say this is 12. This is x, this is y, this is 30, this is 60. It's set up the same way, it's an equation. So I know this is equal to that times the square root of 3. That's the formula. To solve, I'm going to divide by that, and I get x equals 12 over the square root of 3. Don't want a square root of 3 on the bottom, so I'm going to multiply the top and the bottom by square root of 3. Square root of 3 times square root of 3 is square root of 9, which is 3. And finally, I simplify by dividing. That's the hard part. Now, y is whatever double that. 8 square root 3. That's it. Let's try one more of these. $30, $60, $90, 4, A, B. Long leg equals short leg times the square root of 3. Divide 4 divided by square root of 3. Don't want the radical at the bottom. Multiply the top and the bottom. Square root of 3 times square root of 3 is 9, which is 3. I can't do anything else with that. Hypotenuse is whatever that is times 2, 8 square root of 3 over 3. There is also a corollary for this. Corollary to Theorem 51, which says an altitude of an equilateral triangle with sides S is S square root of 3 over 2, and the area is S squared square root of 3 over 4. The reason is fairly simple, but let's take a look. If we have an equilateral triangle with all sides S, and here's our altitude. We know the short leg here, because it's opposite the 30-degree angle, will be S over 2. The altitude is the short leg times the square root of 3. That means the altitude is this, and to find the area, we do 1/2 our altitude times our base, which gives us excuse me, this should be just S, not S over 2 because it's the whole base. See, I still make mistakes. And I get S squared square root of 3 over 4. Once again, any questions, give me a holler. The assignment for this evening is 437, 18 to 21, 26 to 37, 27, 31 to 33, and 444, my favorite number, 6 to 13, 15 to 22, 30 to 31, 42 to 47. Please do not forget that you need to submit your homework to me after we grade them, showing me that you did them and showing me any work. If you have any questions, supposed to be forget 812. Okay, I will see you tomorrow.